The format is that we will have 15 minutes for each of the presentations, and then after this we will have 15 minutes for questions and discussions at the end. And so you can pose your questions in the chat, and they will be organized and then used for the question and discussion session at the end. So I give the word to Javier, who will manage now most of the session.
Hi, good morning, everybody, and welcome to the session. So first speaker is Samantha Wittke from Finnish Geospatial Research Institute, and the title of the presentation is Multitemporal Pixel-Level Coherent Change Detection for Sentinel-1 EWSLC Dense Time Series on the Amazon Rainforest, focusing on the area of Manaus in Brazil. So please go ahead.
Thank you, Javier. I'll share my screen. Just a moment. Sorry, it's loading very long on my end.
Presentation is coming. Don't go away.
Yeah. Before it worked much faster.
Yeah, we tested before, I promise. I see it.
But now it's connecting for longer. Well, anyway, I can slowly start and wait for this to load. Hello, everyone. Good morning. My name is Samantha Wittke. I'm from the Finnish Geospatial Research Institute, and I'm also a doctoral student at Aalto University. And today I will be presenting on behalf of our project lead of the Sentinel-1 for Science Amazonas project, Dr. Neha Yoshi, who is on maternity leave right now. And I will also be presenting on behalf of our project consortium, which you will hopefully see in a moment when my presentation is loading, where we have GSAT from the Czech Republic, NMBU from Norway, Agresta from Spain, and the Finnish Geospatial Research Institute. And it's unfortunately still not loading here on my end. Well, I will. Should I just talk about it without my slides then? Or
yeah, go ahead. Meanwhile,
I also sent my slides yesterday to somewhere, but I will go ahead and
yeah, we just saw it some minutes before, so it's
yeah.
Stuff like this happens with virtual congress. I mean, so go ahead. Meanwhile, we try to resolve it.
Okay. So in the Sentinel-1 for Science project that I will be presenting today, we have two main objectives. The first one is to use Sentinel-1 single look complex IW product to detect forest loss. And the second one is to quantify the carbon loss in these detected areas that have changed. And because of the focus of this conference, I will be focusing on the first objective and show you some of the results and what we have done in using Sentinel-1 for detection of forest loss. For the detection of forest loss, we use both backscatter and the coherence at a 20 by 20 meter pixel size. And I would have had a nice graph showing you that both in backscatter and coherence in the time series of a 6 to 12 day interval, we can identify like when changes in the forest happened in both backscatter and coherence, and also both in both polarizations. And the idea of the project is to capture these changes by some algorithm that can run on a large amount of pixels over a large area at a high resolution. Then to do this, we work in 3 steps. First, we do the pre-processing. I'll quickly try to reload here. No. With the Snap Toolbox to create a 12-day mosaic following the Sentinel 2 tiling system. So we get a coherence and backscatter in both polarization time series. Then for each time step, we extract a set of variables that describe the state of each pixel in time. So for example, we compare how a pixel compares to the previous and future time steps and see if, for example, the change between past and future is significant. And then we call this collection of features that we get a stat cube. And from this, what we call a stat cube, we then try to estimate the forest dynamics. And once we got these stat cubes, we are following two approaches. The first one that I'm going to present today is thresholding and decision tree approach. In the background, we're still working on the slides. And this is designed to be very flexible, both on the thresholding level and also on the decision tree level. Right now, today I'm going to present our results of the area of Manaus, but the algorithm is also running on 2 more test sites at the moment. And that's like the goal, to be able to run it on more than one area and to get consistent results. A nice change map. Then this approach also involves the generation of masks. So it's mostly water areas and flooded areas that will need to be masked out to not detect changes that are like based on this kind of flooding happening in the area. And we use the SRTM data and some country-based land cover classification for that. Then we also do some spatial and temporal filtering and gap filling on the time on the resulting forest change map. The second approach that we have been testing is to use machine learning, since we have a high amount of data and nice time series, basically without gaps. So it has the same. Yeah.
Samantha, can you try to share again the screen? I think it's appearing.
Now the slides are there. That's great. I'm on slide 5, please. Thank you very much. Okay. Sorry for this. And so we test also machine learning for trying to capture the changes from all this kind of data without this step of manually deciding on thresholds or manually finding these thresholds. So the one architecture that we have been testing is the temporal convolutional neural network, which is based on a work by Pelletier in 2019. And yeah, we only had to adjust this for the SAR data. So in this case that I'm presenting today, we use this 16 this 16 parameters in the stat cube for the classification of forest loss, forest change. The next slide, please. Thank you. So as mentioned before, I'm going to focus on the area of Manaus, which is here in the yellow box in the Amazonas basin. We chose this area because, this area is covered by approximately 40 of these Sentinel-2 tiles that we are using, or this Sentinel-2 tiles, the tiling grid that we are using, and it covers about 400,000 square kilometers. And this area experienced a high amount of loss in the last 2 decades, so it is a very dynamic area, so a very good starting point. And the first approach I was presenting, so the thresholding and decision tree approach for this whole area of Manaus takes about 1 week to run on the area. But once we have this this base set, so running on the historical data, once there is new acquisitions coming in, the processing will be very quick. So in the end, it will be like a near real-time processing of and finding the changes happening in the Amazonas. Next slide, please. So here you can see some results of the thresholding and decision tree approach. On the left side, we can see the planet monthly mosaic of, I think, June 2020, where we see this, what we call the ring of deforestation. And then just as a visual comparison, we put here on the slides the Global Forest Watch forest loss data, where you can see in blue what they have detected as forest loss, and then also the PRODES forest loss map in red next to it. I hope it can be seen by you, which is a national level data set where the deforested areas are found manually. Interpretation of mostly optical data. And then on the right, you can see in white the forest losses detected by our thresholding and decision tree approach. And in the bottom, you can see floodplains of the Amazon River. So we have the Amazon River, and then some areas that are frequently flooded. And you can see that, for example, in the Global Forest Watch dataset, some that is very probable just change because of the flooding is detected as a forest loss. Here in the Global Forest Watch dataset, PRODES does not detect anything here. And in our thresholding and decision tree approach, we detect still a few, but much less than what has been detected with optical data. Next slide, please. Now in the bottom, we can see an example of a plantation area and some small scale deforestation. So here we can see that all 3 datasets basically capture the changes happening in this plantation. And but we can also see that our thresholding and decision tree approach leaves some gaps and has a bit more blurry borders than the approaches that are done manually or based on optical data. Next slide. For the actual validation, so this was just some visual comparison to other data sets that exist already. For the actual validation, we have generated our own very large validation data set, which for the area of Manaus is covering 1,400 polygons. And those are based on the Planet optical satellite data that has been released some time ago. And it's based on the monthly mosaics. And here on the left, you can see that we have not only the boundary of the change happening, but also the month when the change happened. And based on these polygons, we try to find, these are used to find, for example, the rate of detection, the average area that we are capturing with our algorithm, and also the false positives, for example. Next slide, please. So with our thresholding and decision tree approach, we get up to a detection rate of the events of 86% with a very low false positive rate. We have a temporal accuracy in a way that the very first pixels that we detect are about 4 months before the event that is marked in the polygon. And the biggest change within the polygon is captured about 2 months later than in the validation polygons. And in reality, this might be a little bit better because if you remember, these stat cubes that we are using, they are already looking at a longer time frame. And also the validation polygons are based on monthly mosaics.
2 minutes, please, Samantha.
Yep.
Minutes.
Thank you. We will. We can also see in the table that smaller areas have a lower detection rate, and the bigger the area that has been deforested, the better our detection rate is as well. Next slide, please. So we can see that there is a good match between like our detections and also other data sets, and also that the temporal accuracy is okay, and we could also see that the small areas could not be detected as well as the bigger one, and the boundaries were also not as crisp and nice as they can be from optical data or when done manually. Next slide. Next slide. Sorry, that one. Yeah, thank you. Then this is a result of the temporal convolutional neural network. You can see in the bottom right row in mostly green. So in the top, we have the planet data from 2016, 18, and then 19. So we see about when the change is happening. We see the Global Forest Watch in the bottom left, and the thresholding decision tree approach in the middle with the pink color. And the results were very promising of this approach because we could see really when a pixel changed with more detail in this approach, and we did not have any spatial filtering here, so also small events were detected. However, also what is in black here is the mask that we used. So if the mask is not perfect, then also our this approach does not work as well. And therefore, we will mostly continue with the decision tree and thresholding approach for this project, and do then the biomass change estimation based on the changes found by that approach. Then next slide. Thank you for your attention. On the last slide, there is also email address of our project lead, Niha, and the website of the project in the bottom right.
Good.
And I'm very happy to hear your questions. And sorry for the technical difficulties.
Many thanks, Samantha, for the presentation and for overcoming the technical issues. So we need to move forward. Also apologize for all the audience for these problems. Hopefully we will resolve it now. And so we'll move forward for next speaker, who is Alejandro Mestre Querada from ISDESAT, Spain. And he will present results on the Syncomap project Sentinel Interferometric Coherence for crop classification. So please go ahead, Alejandro.
Okay, thank you, Javier. I will share my screen now. Okay. So thank you for the introduction. The contents of my presentation are the following. I will start with an introduction of the work. I will very quickly present some theoretical background related to the work. I will then present different classification results based on either coherence or intensity data, and finally some results also based on both coherence and intensity data, and finally I will present some conclusions and future ideas related to this topic. So this work is related to crop time mapping. This crop time mapping constitutes a valuable product of satellite remote sensing because it provides useful information for producers or agencies at either national or international levels. To date, most of crop maps were derived with optical data, but as we know, the quality or the number of images, optical images, might be sometimes limited because of the presence of clouds or haze, for instance, during winter. And in this regard, the use of SAR has progressively gained attraction in the last years because these kind of sensors provide provides consistent time series with almost no gaps, and also especially with we have a better access to the data, especially for instance with Sentinel-1 images. Traditional SAR-based mapping methods were carried out with intensity images, that is backscatter time series. But in this work, we evaluated the use of another product, which is the interferometric coherence. And also it's worth mentioning that this work is part of the ESA SyncoMap project. So very quickly, some theoretical background related to this work. As we know, the coherence provides the correlation between two co-registered SAR images. And when we have a lot of images, that is time series, we can create what we call the multitemporal coherence matrix, which contains all these coherences of all possible combinations of master and slave images. Concerning the classification, we have applied a well-known machine learning algorithm called random forest, which is an extension of the conventional unique decision trees. And it's important to mention that it's supervised classification. That means that we have some known input-output pairs. So moving on to the results, I will present the data set. It's located in an agricultural area located close to the city of Sevilla in the southwest of Spain. And we have used all available images, complex images of 2017, gathered by the two satellite constellations, Sentinel-1 A and B. Looking at the ground truth data, we have 17 different types of crops, which are represented here. We have applied different preprocessing steps to the ground truth data in order to train our model. Firstly, the original ground truth data in the previous slide is divided into a training set and a testing set. The training is used to build the model, and the testing set is used to evaluate its performance. And this is done in such a way that half of the fields of each crop type are assigned to each set. Moreover, the training set is balanced. That means that we have the same number of pixels of each class. This is done to avoid biased classifications toward majority classes. So we will use this equally subsampled training set. Concerning the preprocessing of Sentinel-1 data, we have used conventional in-SAR processing, means co-registration of all images, calibration, generation of the interferometric stack of both available polarization of Sentinel-1, VV and VH, and we have applied the speckle filtering and coherence estimation with a conventional boxcar filter. Finally, all these SAR data are reprojected into a common cartographic projection in order to match with the ground truth data. Okay, so moving on to the results, I will start with the coherence-based classification. As shown with the confusion matrix represented here, the coherence only provides globally good results using 6 days coherences at vivid polarization. However, 5 classes still have a low accuracy, and 2 classes present very low accuracies. We have done different tests in order to evaluate the influence of the quantity of information, or in terms of the temporal baselines. When we use coherences coming from 6 days of temporal baselines, the accuracy is higher. However, when we use coherences coming from longer temporal baselines, the accuracy progressively decreases. Also, in terms of the influence of the temporal baseline, we have shown that if we add more baselines, that means if we add more data to train the random forest, the accuracy is not improved. In terms of polarization, we have also evaluated its performances, and in this case, in terms of coherence, DD channel works better, since the accuracy of each class, as shown with the confusion matrix here, decreases when we use only VH polarization. We have more confusion between classes. However, it's important that when we use both channels, the accuracy is always improved. The confusion is reduced. So as a summary, the best result obtained with only coherences is obtained with both polarizations and 6 days of temporal baselines. We obtained a very remarkable overall accuracy of almost 80% and a kappa score of 0.73, as shown with in the table, and this is the predicted crop map. In terms of intensity, we have more or less do the same test. We have evaluated firstly the quantity of images. The best result is obtained when we use all available intensity images, which are 60 images. However, when we use a less number of images, 1/2 and 1/3, accuracy goes down, shown in this table. We have also evaluated the performance of the classifier in terms of classification with intensity data. Contrarily to coherence, in this case, VH channel provides better accuracies. This was expected because VH channel is used to have better sensitivity to the vegetation. And again, when we use both polarizations, the accuracy is always improved. These are the confusion matrix obtained with after using all the 60 images. So again, as a summary, when we use only intensity, we obtain a very similar results to the one shown with obtained with the coherence. We have again an overall accuracy of almost 80% and the same kappa score, which is quite remarkable. So the last results were obtained using both coherence and intensity as input to the random forest algorithm. We have selected the 6 days coherences and all the intensity images, since they provided the best classification results. So when we use all this data, we are able to obtain higher accuracies of all classes, either only single polarized data, either VV, VH, and especially when we use both polarization, the accuracy is greatly is increased. So we have all classes now present an accuracy higher than 50%, and all of them, or a lot of them, higher than 80%. So as a summary, this is the best results that were obtained in this work, which were obtained using both polarizations of Sentinel-1. We move now to more than 85% of accuracy, and the kappa score is also greatly improved. If we compare both the ground truth data and the predicted crop map, they are very similar, which is quite remarkable. So that we have proved that the combination of these two inputs to the random forest works very well. But we have finally what is the reason why this is working. We think if we look at this slide, we see we are plotting the temporal evolution of each crop type. We see that they are quite different. That means that each crop type has its own temporal evolution, which is in relation with the planting and harvesting time. So this is what this different temporal evolution is what is the reason why the algorithm is able to distinguish between each class. The same plots could be done with the intensities. So finally, as conclusion of this work, we have shown the potential of Sentinel-1 coherence and intensity data for supervised classification. We have seen that in-SAR data, means the correlation between two images, are also sensitive to the temporal evolution of crops, and they constitute a solid source of information on its own for classification purposes. However, they are indeed a complement to traditional intensity-based classification, since we have seen that if both features are simultaneously used, there is a very significant increase of accuracy. And also, we have seen that the polarization is important, since if we use both channels at the same time, the accuracy is always higher. In terms of future work in this topic, it would be interesting to evaluate the influence of more sophisticated speckle filters and coherence estimators, like non-local approaches. And also, it would be interesting to evaluate the performance of deep learning methods, which are very used nowadays. And also, it will be interesting to develop a theoretical model of coherence in terms of decorrelation sources, for instance, the signal-to-noise ratio decorrelation, or the temporal baseline, the temporal decorrelation. And finally, more details of this work can be found in this published paper in this journal. We have put a link to the DOI and the webpage of the document.
Thanks.
And that was all. Thank you for your attention. Sorry.
Thanks, Alejandro. Many thanks for this great presentation. So we are some minutes behind schedule, so we need to move forward to the next presentation. But I will encourage the audience to please launch the questions there in the panel, and will be addressed at the end of the session. So please go ahead with the questions. So next speaker is José Luis Hueso-Bello from DLR. Presenting the title Towards the Monitoring of the Amazon Rainforest with Tandemics and Deep Learning Strategies. So please, José Luis, go ahead. I think we cannot hear you. You are in mute.
Now? Yes.
Now, good. Yeah. Go ahead.
Okay. And Ryan. Okay. Perfect. Exactly. Okay. Thank you very much, Javier. As you read, I mean, we are now, changing so a little bit the satellite. I am going to present so also similar to the previous presentation, concentrated on the Amazonas rainforest, but using so deep learning and with Tandemics. Please, next slide. Next slide, please. Mm-hmm. Okay, exactly. First of all, I'm going to the other slide, please. The previous one. Okay. I'm going to briefly introduce, for sure for the audience is well known, the Tandemics interferometric data set. Tandemics is so a mission with two satellites flying in controlled close formation. Okay, sorry for that. Yeah, I'm just going to briefly introduce the Tandemics interferometric data set. I'm going to present also the previous results of the global forest non-forest map, some previous investigation with the convolutional neural network-based forest mapping with TandemX, and then to focus on our results and work on the Amazon rainforest monitoring, with finally the summary and outlook. Please, next slide. Exactly. The TandemX was acquiring data from end of 2010 up to the present. More than 500,000 images were acquiring for the generation of the global DEM, which implies at least 2 global coverage. There are in some difficult terrain regions as mountains or desert, up to more than 10 acquisitions. And each nominal interferometric resolution of each image is 12 meters, which implies more than 350 megabytes per image. Here we see the final TandemX DEM, global DEM. Exactly. Please move to the next slide. Exactly, but there is a multi-look and requantized version of the full resolution to a ground resolution of 50 by 50 meters, which is very helpful for performance monitoring and acquisition planning, have been used during the world mission. And this implies just a reduced computational burden of just 1 megabyte per image. This TandemX quick look data set, we have available all. We have the DEM, we have the amplitude, the coherence, and that makes the quick look data set very interesting for global planning. Next slide, please. Exactly. Here we have an example of a quick look mosaic obtained with TandemX. Here is shown the interferometric coherence, which the interferometric coherence is well known, maybe approximated with different terms accounting for different influences. And if we next slide, next slide, please. If we take a look on the volume correlation factor, which usually is can be not distinguished from the temporal decorrelation in most of the SAR sensors, but in the case of TandemX, since they are acquiring bistatic acquisitions, the temporal decorrelation is 1. We don't have. And then estimating the total interferometric coherence and all the other parameters, depending on the ambiguities or the quantization, the SNR are known from the system engineers. The gamma, the volume correlation factor can be estimated. And as we can see in this global map, it seems that and this is also well known, that the gamma ball exactly. We see here, I mean, I just talk and hope that you get exactly. This is so so a previous work where we classify using so tandem mix. So all images acquired for the global DEM based on a supervised clustering approach. Here we have the example of an image of the volume correlation factor, and from there we estimated using this algorithm the membership of this. I mean, just distinguishing between forest and non-forest. We mosaic all overlapping acquisitions to achieve so good classification accuracy, and even we use so some external layers were necessary, for example, to filter so water bodies and cities. This is the baseline approach. Okay, and exactly, here's the final product that we obtained, the final map, which is available for download on GeoService of the German Aerospace Center. Please, next slide. There is also some preliminary work with using so convolutional neural networks for forest mapping with tandem mix. In this study, they use 3 different CNNs configuration were investigated, and also so different possible combination of the data set, tandem mix data set. I mean, amplitude, coherence, incidence angle, so different of the features were used, and the study was concentrated in a region of Pennsylvania in the USA, where we have so a good reference available of a resolution of lower than 1 by 1 meter. This was so temperate forest, and the analysis was done on single images only. The winner of this, please next slide. The winner of this study was a classical unit with encoder, decoder. I mean, this is well known in machine learning, in deep learning. And then what we did in the actual work is we extended the input features. We use the interferometric coherence, the amplitude, and we extend it also with the height of ambiguity and the local incidence angle. Also, we extend the output, not just to classify so forest and non-forest, also to taking benefit of the environment of the Amazonas rainforest to classify also water. The unit was trained from scratch to avoid any type of transfer learning, and we use an ad hoc training strategy for model generalization all of the different acquisition geometries. Please, next slide. Here are some insights on the CNN training strategy we use. As reference, we use so forest map based on Landsat from 2010 to characterize all the different tandem mix acquisition geometries. We use also images from 2011 and 2012 where necessary, and also because these ones are close to the reference data, we end up using 455 images for training, where we divided them taking into account different ranges of incidence angle, as it was done for the tandem mix forest non-forest map. Also, we consider height of ambiguity between 20 and 120 meters, and we try to have a balance class training looking for images with a forest content between 30 and 70%. We would use extra images to train the unit on the detection of water. Please, next slide. Here we have the height of ambiguity, the variation, where it is over the data takes over the Amazonas rainforest, where it's clearly visible. So around 2011, for the first global coverage of tandem mix, the target height of ambiguity was around 50 meters, and then in the second year of acquisition, so around 2012, this a little bit smaller, so around 35 meters. That was driven by the performance of the DEM. Next slide, please. We use 320 images were considered for the testing of the CNN with similar characteristic as the ones used for the training. Here we have the results of both of the clustering approach in red and of the unit of the convolutional neural network, so in blue. And we see that so as soon as we achieve so a 20% of forest with the CNN, we achieve so one score of more than 0.8. And also, especially when we look for dense forest, the unit seems to better classify the forest. Here we have so the mean values we obtain, which yeah, I mean, this is a significant so improvement of the CNN with respect to the clustering approach. Here we have so we use different images. Next slide, please. Different images over the same test area. This is what the so-called so long-term system monitoring areas, where we have so acquired so images with different so height of ambiguity. And here is also clearly visible that so starting by a height of ambiguity of 90 meters, the CNN performs much better than the clustering. If you click, please, then you will see here we have an example for a height of an images. I mean, on the left is the reference, the Landsat, on the middle is the clustering approach, and on the right, the CNN. We see that for a height of ambiguity so close to 50 meters, both performs very good. Please click again. Then here we have so for height of ambiguity so more than 100 meters, that the CNN performs much better than the clustering approach. Click, please, again. Here we have so
2 minutes, please, José Luis.
Okay, I will be fast. Okay, here we have so the results over more than 1,000 images over the Amazonas, where we have so this mean F-score improvement of 0.13. Here we have also, next slide, please, the water detection, where we see so different so water bodies. I mean, so rivers on the right, and so lakes on the left, and the classification looks also so very good. Using the same data set that we use for, next slide, please, to create the global map, we end up so generating over the Amazonas so three different mosaics. One for 2011. Next slide, please. One for 2013. Next slide, please. And one for 2016, where we see that this is not really a global coverage, but the Amazonas was well covered, especially the regions where we have so deforestation. We compare our map with the from GLC, which has a 10 by 10 meter resolution. It's based on Landsat imagery up to 2015 and was updated with Sentinel 2 in 2000 to 2017. And we compare, I mean, the Tandemix or mosaic of 2013 and the one of 2016. So achieving so for an overall accuracy close to the 90%. And we see that for the different so land cover classes, forest is the best one performing. Water, we have so some problems due to the resolution, that this is not sometimes not able to distinguish small rivers. In between the vegetation, and also for non-forest, there are so some regions close to the rivers where it seems at X1 we see only, I mean, not really so dense forest. This is as another kind of forest, and we detect it as non-forest. Here we have an example of so looking at Google Earth, the Tandemix, so there's the 2016, this is in a geocell 1 by 1 degree, and from GLC, and this is a very good so in accordance. And why we title, so the title was towards the Amazon rainforest. Here we have so Landsat and also so Google Earth on the top, and we see how it's possible, so able to distinguish the clear cut. Let's next slide. Here we have so a zoom of the three mosaics we generated, where it is possible so to see so Google Earth as well as the classification using the unit, and as well as the detected clear cuts. Finally, there is so a significant performance improvement by using so deep learning strategies. Moreover, it's possible to classify other kinds of land covers, also looking for water. it makes possible to skip the weighted mosaicing of overlapping images. That allows us also, as I said, not just to have one map, to have three different ones. There is a high agreement with other land classification maps, and of course, once the unit has been trained, may be so extended to other tropical forested areas. Sorry, I mean, thank you very much for your attention. If you could follow, and sorry for the problems with the. It was my fault. Sorry.
You're welcome, Jose Luis. You made a good job. Great presentation with results. I think great accuracy numbers, and with such impressive mission, tandem mix, for topography changes and so on. So let's move forward because we're behind schedule. So come back to Sentinel. Vinet Kumar from Delft University will present Sentinel-1 interferometric coherence for crop growth monitoring in the Netherlands. So please, Vinet, go ahead.
Yeah, thank you. I will just share my slides. Just a moment. Yeah. Yeah, so it's visible properly. Thank you. Yeah, hi everyone. Good morning. I'm Vineet Kumar, postdoc as Delft University of Technology, Netherlands, and I'm going to present on topic Sentinel-1 SAR interferometric coherence for crop growth monitoring in the Netherlands. And along with this, I would like to introduce my co-author, Manuel Haber and Don Roman from ESA's Tech Netherlands, and Susan Steele-Dunn from Delft University of Technology. Yeah, so sorry, I cannot move my next slide. Yeah, okay, yeah, it's working. Okay, so motivation of work is to understand parcel level crop dynamics from the remote sensing observation is very important for decision makers, for farmers or agriculture growing organization, because it helps them in taking a within field decision, which is going to ultimately help in precision farming or sustainable use of resources. So with the launch of Sentinel-1 and in a high revisit and high repeat cycle, Sentinel-1 supports near real-time monitoring of agriculture activities. However, there are some barriers which pose challenge to application user as well as sometimes to the expert domain user to process the Sentinel-1 SAR data because of its volume. As we everyone know, the GRD product comes around 1.5 GB and the SLC products around 7.5 GB. So if one wants to do monitoring at national scale or even a smaller scale, but with a large dense time series, they face a lot of problems with the data volume, computational demands, and processing of SAR data. So these are the few barriers which are posing challenges. So in this study, we try to provide a solution for this with a framework and also the Sentinel-1 interferometric coherence is underused or relatively less used comparison to the backscatter coefficient for agricultural monitoring related activities. So in the next slide, I'm going to present how a framework parcel level Sentinel-1 data framework can be made with the backscatter data, and I'm going to show how a prototype for coherence data for parcel level crop monitoring. So the framework, or we can say a database we have produced is Agricultural Sandbox NL, and this processing has been done over the Netherlands. The choice of Netherlands is because openly available geospatial data sets, such as BRP crop parcel base register that informs about the individual parcel information in terms of object ID and then the crop geometry and the associated let long information from 2009. And it updates annually for each year. So this is a very huge database, and we can see there are around 770,000 parcels in the Netherlands approximately for a year. So we have produced this database for all the 770,000 crop parcels using approximately 3,000 Sentinel-1 GRD images in 6 different relative orbits, which overpass over the Netherlands. And the processing has been done in the Google Earth Engine and with a tool GMap and the Python. And in response, what user can get from the database. So if they want to query it field-wise, if they want to query it administrative boundary-wise, or if they want to see parcel level time series information, or let's say if they want to see a crop map for particular date of entire Netherlands using the backscattering coefficient, they can run it through and they can get it without being hindered by the processing issue, because we have already produced this database. So for this, we have processed approximately 5 TB of data, and the output database for 3 consecutive years is around 12 GB. So just to remind, this database we have created with the Sentinel-1 GRD data products, which are available in the Google Earth Engine. So on the similar line, we try to make a database for Sentinel-1 Interferometric Coherence. And so we made a prototype over the province of Flevoland in the Netherlands, and I'm going to show that in the next slide. So to show similar kind of database, but with the interferometric coherence, we have processed 32 pairs of or 64 images of Sentinel-1 in 2019, in particular to relative orbit 110. And the processing has been performed in the SNAP using the standard interferometric processing methods, and over the Flevopolder region of Flevoland province. And then 32 pairs of coherence map in the TIFF format has been generated. And the processing time we have chosen from April to October 2019. That is the typical summer season in the Netherlands, summer crop growing season in the Netherlands. Then these coherence map imported into the Google Earth Engine to create a similar database like the GRD product. So we processed these coherence map according to the BRP shape files of the Flevoland. So there are around 11,000 crop parcels in the Flevoland, and we processed them in Google Earth Engine and then created a database using Python, which is a parcel level interferometric coherence map, which are spatially averaged for each parcel and over a period of time. So how now we have the database, that is interferometric coherence parcel level database. Now how one can query or user can query this database. So as I mentioned earlier also, and again here, so one can query like for individual crop parcel with a given object ID of that particular crop parcel. Then plot a time series in VV and VH coherence. It also gives, the database also gives PV VH coherence that is partially averaged for a parcel level, and then standard deviation also, and the static information of the field. So user can query for individual parcel, then they can query by aggregating over an administrative boundary of the region, and they can get the map for particular date. So parcel level coherence map, let's say in the summer season, in the peak crop growth season, and the late winter season. And as I mentioned, so there was 64 SLC images were processed, and the resulting database size, which is in either in NetCDF format or in a pickle format, is around 30 MB. So it's very useful and handy to process and get the information without hassling with the computational related issue. Now, in the next slide, few slides, I'm going to present few result and potential application where this parcel level interferometric coherence can be used. So the first one, which is I'm going to show here, is the mapping crop emergence date in VV pole coherence. So here we can see a crop classification map over the flavopolar. So I'm just showing here the major crop classes because there are more than 100 crops, different kind of crops they are grown in the region. So we can see clearly from this right-hand side coherence map. So the first map is, the top map is from early date of April, and we can see a very high coherence value. So these are due to the crop management activities going on before the planting, crop planting. So such as tillage or crop field plowing. So this leads to a very high coherence. So, and then in the May, when the crop gets emerged from the field, so the coherence slightly reduced in comparison to April. So one wants to identify the emergence date, they can select particular pair, or they can select particular interferometric coherence map to see the get the information about the crop emergence. Moving forward, yeah. So as the crop season progresses, like from early vegetative or emergence to the vegetative phase of the crop or the peak biomass phase of the crop, we can see here the coherence value reduce. So the reduction is coherence due to change in the plant, like we made the coherence map between two 6-day pairs. So this is due to the crop growth during that time, or possibility of movement of the scatterers from the crop. So scatterers such as leaves or stalks, or there is a change in the moisture content in the soil as well as in the crop. So this shifts the scattering center while observing from the SAR data. Hence, the interferometric coherence values are low during the biomass, peak biomass, or vegetative growth of the crops. However, we can see some fields which are very high in the coherence value. So we try to identify them, and these are the winter wheat parcels. So winter wheat, the crop growth cycle of winter wheat is slightly different. It get harvested from mid-July to early of August, and we can see after harvest there is a high value of coherence. So indirectly we can identify the winter wheat crop in a peak summer cycle of other summer crops. Then moving forward to next slide. Yeah, so we can detect the harvest period using the interferometric coherence. So the maps which I'm showing here is from September and October 2019. So which is a typical crop harvest season in the Netherlands. And we can see increase in the interferometric coherence value, which is more than 0.5 in the month of October, and between 0.4 to 0.6 in September. And so after the harvest, so just before the harvest, the coherence value is minimum, but after the harvest, in around 10 days, the coherence value gets increased. So by identifying those particular high coherence value, we can determine the harvest date using the interferometric coherence. And also we can see even in October, there are fields or parcels which are having a low coherence. So these are the grassland parcels, which is having a quite same kind of growth throughout the year, except some mowing or logging events. So we can see these grassland parcels again very clearly in the coherence maps.
2 minutes, please. 2 minutes.
Okay. So coming to monitoring the difference in the different crop growth. So we have related the VV coherence with the existing VV backscatter and cross-pole ratio. So there is already literature which states that the coherence is inversely related to the NDVI values. And we can see here the coherence again somewhat inversely related to the cross-pole ratio. So in this slide, I'm showing you we can differentiate with the coherence two structurally same crop, that is potato and sugar beet, but they are having different phenological cycles. So that we can see here. And then the last result, that is monitoring the crop phenology with the coherence. So we can clearly see here from the first plot, that is coherence, a high coherence prior to the emergence and a very high standard deviation due to the management activities or the row orientation of the field. And then this coherence reduces in the vegetative stage and reproductive, and then again the coherence value increase after the harvest. And we can relate this interferometric coherence with the cross-pole ratio as shown here, and somewhat to the VV backscatter coefficient. So concluding my presentation, the time series coherence is useful for many agriculture events such as emergence, harvest, or phenological chains. And it can work as a complementary data to the backscatter and sometime with the optical data set also. And the overall objective was of Agriculture Sandbox Channel to make SAR data accessible for new, non-expert as well as expert user to generate or to avoid the computational processing challenge and relate this SAR data with the openly available geospatial data sets. And we also included a prototype of coherence to show different use cases. The ongoing work on this to create a similar national level database for coherence for entire Netherlands in all the different orbits. And the details of this work can be found in the this below mentioned publication, which is under review in Nature Scientific Data. And the data is the database is openly available through 4TU Research Data Center and can be downloaded from the given link. Thank you, and thank you very much for listening.
Thanks. Many thanks, Vinet. Great presentation, great work. So we need to move forward because we are late behind schedule. So we'll move to the last presentation of the session. Now coming back to Tandemix. So speaker is Michael Schlun from University of Twente. And the title is Above Ground Biomass Changes in a Tropical Landscape Revealed by Tandemix Inter-Height Model Differences. So please, Michael, go ahead.
Yeah, the share content button is still grayed out. I wait, I guess, for the rights to share my screen. Now it's there. All right. I hope you can see my screen now. And I go ahead. As mentioned, the title of the presentation today is Above Ground Biomass Changes in the Tropical Landscape Revealed by Tandemix Inter-Height Model Differences. And of course, this work is not only based on only my person and myself. I also thank all my co-authors who did a great job, especially with the ground truth in Indonesia. To introduce you into the topic, as mentioned, we talk again about Tandemix, so about X-band INSAR heights. And normally, what we assume or people assume is that the penetration of an X-band INSAR system is quite low. So we basically represent with an inner height the canopy surface height, as you can see here. And of course, this means if we now acquire the expand inner height multiple times, and we can use that then for monitoring of forests by comparing these different inner heights. For example, if we can see it here now in this extreme case that a few trees were removed or harvested, then of course we see a drastic decrease in the inner height, which can be then detected as a forest change here. And again, also we think that, or normally people think that the canopy height or the surface height is also linked to the biomass. And of course, in turn, this means also that this biomass change or is also linked to the inner height change, or the other way around. Yeah. So with an inner height change, you can then basically estimate also above ground biomass change. Therefore, we set up a project and a workflow which can look like this. We have a tandem X acquisition at time step 0, where the forest is still intact. We create then, according to the tandem X and DLR processor, the inner height with a lot of additional and auxiliary information. And we do this then a time step later, where we assume there is a change. And we compare now these two types of information. Of course, usually it doesn't suffice to simply compare the inner heights, but we also need to understand the sensitivity of this inner height changes and compare it also to ground truth. So therefore, we did a sensitivity analysis with a few auxiliary information, ground truth, and especially also acquisition parameters, which can be retrieved from the tandem X acquisition. And finally, we have then the change information with a lot of quality information in the background. As mentioned, we need a lot of ground truth data for that, and therefore the project was associated to the efforts project, who was responsible also for the ground truth data. Now I go into one specific example of such a project and above ground biomass change example. We did an example in a dynamic tropical landscape in Jambi, Indonesia. And as you can see here in this map, we have first a few ground truth points here acquired as plot data, but we have also LiDAR acquisition, which can be also used as a reference here in these grayish areas. What you also can see is that the area is a mosaic of protected forests here depicted in this green shaded area here. We have also some large oil palm concessions, and in between we have some smallholder farms which also grow then basically oil palm and mainly rubber. What we already saw before we did the analysis is that the expand or the settlements and smallholders already expand into this protected area, but we can also see this then later in the inner height difference. Now coming to the data, we use the bitemporal tandem X data sets, basically from the global tandem X acquisition in October 2012. And then we use another acquisition from the so-called change stem acquisition phase from February 2019. And in line with that, we have also inventory data, which was acquired at the same time from the tandem X acquisition. So this is a really great data set combining these two together. And what you can see in this tandem X acquisitions, so most of the parameters, the height of ambiguity and effective baseline and incidence angle, are quite similar and comparable. The biggest difference is the orbit, and with that also the look direction. And as I mentioned, we have a LiDAR data set, which can be used then as a reference, at least for the second tandem X acquisition. Of course, in the first step, we retrieved the inner heights. As mentioned before, we follow basically and used even the global tandem X processing scheme from DLR. And here you see just a visual comparison between the LiDAR surface height model and the tandem X inner height model. which basically show quite coherent results, so they are quite accurate. And we also try to assess the accuracy of these in-the-height models with the LiDAR. And here in no vegetation, we saw a relatively good accuracy of the Tandem X acquisitions. And of course, in vegetation, we see, due to the penetration into the volume, but also due to the volume decorrelation, a lower accuracy with about 8 meter RMSE. But then in the next step, we basically ignored, let's say, these penetration effects and simply calculated the differences between the two Tandem X acquisition and INSAR heights, which is, can you see here then? And in the next step, related this Tandem X INSAR height differences to the biomass differences estimated in the field. And as you can see it here, we see over the different plots relatively good linear regression, but this is mainly based on a few extreme cases here where we have a lot of deforestation or decrease in above ground biomass and growth also in above ground biomass. But in this, let's say, smaller change areas, we see a lot of scattering here, but still in total, we have a relatively good R squared. Now, if you think about what can be the source of errors here in these smaller change areas, I think it's good to show it again in a profile. The penetration of Tandem X here, as can be seen, compared to the LiDAR in grayish and black areas here. And in the reddish, you see this, the Tandem X heights basically, and we see a lot of penetration into the volume and into the forest. And if we now think about, if we now compare two Tandem X INSAR heights, and they have different penetration into the volume, then of course this difference in penetration propagates then also to the INSAR height differences, and also then of course into the relationship to the biomass difference. So therefore we try to somehow approximate or make a first order approximation of the penetration depth, assuming that the volume is a uniform scattering layer. And therefore we thought that, or we assume that the interferometric coherence is basically linked to the penetration depth, and used a rather simple model to approximate the penetration depth. And basically added this information of the penetration to the original INSAR height. And now you can see that somehow it follows, in most cases, much better the reference LiDAR surface model. And we did this, of course, for both acquisitions, and now they are more comparable. And this propagates now also into the relationship to the biomass. Here again, the original one without the approximation of penetration depth. And then if we approximate the penetration depth in these INSAR height differences, then we see a much better relationship. We see still a little bit scattering in these smaller change areas, but it's much improved. And also the R squared improved in this relationship. So here you can see then above ground biomass change as a then scaled to the whole area, and we see a lot of changes in some, or substantial changes in the oil palm concession, which are renewed. But here you see also a lot of changes in the forest area, and as mentioned, we saw this expansion visually in the Landsat image, also in this protected forest. So in general, the INSAR difference indeed is related to the biomass difference, but the penetration and also even other error sources, for example, if you look at the different orbits and different look directions, could also propagate to different error sources, and or can be an error source, and we have to somehow account for that. And in this study, we basically account now as a first order approximation to the penetration depth differences. And we saw an improvement in especially the relationship with an R squared of 0.5 improved to 0.65, but also the error improved from 15 to 13%. To conclude, again, as mentioned, the inter-height differences has high potential to estimate above biomass differences, but to really get a very good result and good accuracies, we have to account for different error sources. As I mentioned, we did it here now for the penetration depth, but I think there are even more, and we have to account for that to really get very accurate results. But in general, we can use this kind of information, the inter-height differences, which is related to forest structure differences and above-ground biomass differences, can use that information potentially to understand ecosystem dynamics. Here, as shown in this example, in this Indonesian case. And also, I think the results are very relevant for different acquisition phases of Tandem X, for example, the Tandem X change stem acquisitions, but also for future missions with bistatic INSAR capabilities, for example, the high-resolution wide swath mission. And with that, I thank you for your attention and open for any question. Thank you.
Many thanks, Michael. Great presentation and indeed very interesting application. And so we need to move forward. Just would like to thanks to all the speakers for the presentations and for the great job. And I leave the floor to Urs to manage the question and answer session right now until 11. So Urs.
Thank you, Javier. So we have now time for questions and answers. And as I understand, I should get a list of the chat questions you post summarized. Maybe until I see this, I can personally ask a first question to the last presenter. Michael, you mentioned that you included both one Tandem X data set was with ascending orbits and one with descending orbits. You did not really show then anomalies you encountered. Can you comment on this, if this is problematic to combine the two directions?
It can be, of course, problematic if you go into a different or let's say rugged terrain, for example, in topographical areas. I mean, this area is relatively flat. Where we encountered problems is, of course, at edges of forests. So if you look from the one direction, it can be then like a shadow or something else. But if you look now from the other direction, it can be something different. So we saw a few errors in forest edges, but in general, I assume, and if you look in let's say more area of forest, then it's quite okay, I think, at least in this topographically flat area. So as a first study, and I think the most problematic thing is, of course, to get this repeated inventory. So we kind of fixed to this area. We didn't encounter so much problems, so it was good for first case study. But I assume if we go now in a more broader scale, and then of course we will encounter even more problems, I guess.
Thank you. Okay.
So Urs, I'm recovering one question from the audience at the beginning of the session for Wittke. They asked, Kevin asked if Wittke, if you were using radar data for masking the flooded area mask, for retrieving the flooded area mask. So leave the floor to answer the question.
Yes, thanks for the question. So for the masking of the flooded areas, we basically create a base map of water areas in the beginning of the study time, so in 2016, with ancillary data, so land cover maps, the water areas, and also SRTM. And then when a detection of a loss is made, then we use the backscatter and coherence and set basically a threshold and see if that is water, also based on the Sentinel-1 data. So yes, we use it.
I see a question for Alejandro here. How much this approach is sensitive to the number of training samples? Availability of large number of known pixels is often challenging in practical cases. Can you please answer?
Yes, thank you for the question. Well, in this case, we had like a perfect or very complete ground truth, which was done manually by the local administration. So we were able to evaluate the influence of the number of training samples very well. Moreover, as we know, the number of training samples greatly influences the results. Of course, the larger the number of training samples, the better is the result, but we will certainly have overfitting effects. That means that the model will be very prepared for this specific data, but not to unknown data. In order to avoid this, instead of just selecting randomly a given percentage of pixels, 10% or 1%, we followed the strategy of the preprocessing of the ground truth, which was presented. We divided the ground truth data into a testing set and a training set, with half of the fields assigned to each set randomly. And finally, the training set is balanced in such a way that each class had exactly the same number of pixels. In terms of numbers, I guess it was around 2% of the total number of pixels which were used for training.
Another person asks you, what was the size of the multi-looking window for the coherence estimation?
Okay, so the number of training samples, the multi-looking window was 9 pixels in azimuth and 19 pixels in range. This yields an output pixel resolution of 60 by 80 meters, taking into account that the original resolution of Sentinel-1 was 3 by 22 meters. This provides a good balance between loss of spatial resolution and accuracy estimation of the coherence. And it's also important that this boxcar filter was also used to reduce the speckle in intensity images.
Thank you. And a question to Vinet. Nice talk. How do you tackle the presence of very low coherence in pairs coinciding with rain events? Do you detect, remove them somehow?
Yeah, so thank you for the question, but I would like to clarify here the objective of this project is to create a kind of database with a 6-day interval, 6-day interval interferometric pair. So we have generated a pair without considering this effect, but yes, the rain, if it happens on the same day of the Sentinel-1 acquisition, it is going to affect the coherence. So we can, in the analysis part, we can reduce or remove those pairs by using some threshold methods. And another point, we haven't used it in the processing part because we want to cover as much as large spatial area. So there are chances in some part there is no rain, and in some part there is a rain. So we would like to remove those pairs in the post generation part or in the analysis part.
I also have a point of discussion or question to you. In your introduction, you mentioned as the great barriers, the data volume and how much computing has to be done. I disagree on this. I think these are technical things which can be solved, and there are great computers and so on. But to translate the coherence time series and the backscatter time series into crop information, in my point of view, that is the challenging or difficult part. I fully agree that there is a lot of information, but I think there our competence is needed, and not so much as computer specialists in being able to download big data sets and so on. What do you
I agree on some part with you, but the thing is like if someone wants to use it on a local machine or on a small like let's say low powered or low RAM computer, then there is a problem because of the size of the data, and while we process, then they face the problem. So our objective was to create a such database. Then we can build on either the expert user or the application user who just want to use the parcel level information, parcel level backscatter or coherence map to build something on it. Let's say the biophysical parameter estimation tool or the grassland monitoring tool or decision for precision farming. So so the first thing is something is already there. They can they need not to do the processing part or other data handling part and built upon it. So I agree on that part. Yes, there is a need to build something over the parcel level backscatter that directly relates to the agriculture, such as soil moisture estimates or biophysical parameter estimate.
Thank you.
Thank you.
Okay, are there other questions?
Yeah, there are a general question from the audience. What important parameters we should consider before rolling the system you mentioned for developing nations to help agriculture industries? So it's a general question that perhaps we can move for the panel discussion we have in the afternoon. So in the meanwhile, I would like to encourage any of the speakers if they want to take the floor and give thoughts on this.
Sorry?
So there is a general question about what important parameters we should consider before running the system. So probably one of the important parameters is the training data. So when we focus on crop classification and crop monitoring, training data and the identification of parcels is a major issue. And I wonder that this could be one of the important parameters. And the other one is the systematic availability of data. So having continuous sampling as much close as possible in time, it's a major issue when we focus on crop monitoring. We saw that the improvement when we reduce the time gap between acquisitions from weekly to 6 days, or probably short to 1 day, it's terrific, and that could be two key parameters. Yeah, there is a question from B that we missed. I think did you, Binet, the audience? Yeah. Did you compare amplitude with coherence? And the other one is what is the use of coherence if it can be done using amplitude data?
Yeah, so there are certain applications which, like we did a qualitative analysis here for this study that, let's say, for example, potato and sugar beet were there. So the VV backscatter in particularly not able to differentiate them, but with the coherence we can easily differentiate these type of two crops. And in particular, the events like harvesting date. So that is quite clear with the emergence in comparison to the backscattering coefficient. So, and I would also like to add here, the information is complementary. So it's not something coherence can replace the backscattering coefficient, but it can add on to the existing information.
Okay.
Yeah.
So I think that's all. We are behind schedule, unfortunately, and we need to stop the session here. So thanks for all the speakers once again. I think it's we miss a lot the warmth of the audience. So clapping the hands of the people, and thanks a lot also for the audience, for the patience, and for supporting the program we had during the session. So it was a good session, and so let's close it here.
Bye-bye.
Bye-bye.
Thank you all
Bye.
for your
Thank you, everyone.
participation. Thank you.
Okay, bye-bye.